Okay. Kind of a glare on my screen here, but that's okay. Since we talked about categorical data last day, I recorded this snippet and I couldn't find a clip online, so I had to actually stand in front of my TV and like old school film it. So the quality is very poor, but this is to support why we shouldn't use pie charts, because if we use pie charts, they're really only useful if we have just two sections of the pie chart. And so, but then you can just communicate it with one number, as in, so if you're not familiar with Superstore, they've got a lot of funny stats jokes in there.
You don't think people in this store do marijuana, do you?
I mean,
Probably.
How many of them?
Like half.
Wait, half do or half don't?
It's both.
okay.
Anyways, pretty cute, pretty funny. There, that's my funny for today, I guess. We're going to start probability, but just do a little recap of summarizing categorical data. There isn't a lot that we can do with categorical data, and I did just kind of rip through it last day. And then I promised we'd review it, and we will see more of the contingency tables today. And so, as promised, we will be working through it. But so I wrote out the review already. We talked about summarizing categorical data. We finished talking about summarizing numerical data. There's a lot more that we can do with the numerical data. And I just had a little moment. Did I record? I think I did. Yes. Okay. Phew. Okay. I feel like every class I have a moment where I'm like, did I forget to record? It's pretty early on today. So we can summarize categorical data. We can summarize it visually, which bar plots are best, right? And so there's a lot of different reasons why we shouldn't use pie charts. All right, so here, do not use pie charts. They are an option, right? And they're tempting just to spice things up in your report, but you should be using bar plots. There's a lot of studies have been done where our eyes do a really good job of discerning differences, even small differences in the heights of the bars, which is the point of visually summarizing categorical data. And so, right, each bar is the count or a proportion in each category, and doing the same with pie charts is difficult, right? You'd have to have all these labels, and if you have lots of groups, then it's really hard to read. Okay? And so do not use pie charts because they are often hard to read. Unless there are only two groups, right, or two categories. But then, right, if there's only two categories, then I just need to tell you the number for one, and then you know the other half, right, or the other proportion. To summarize categorical data numerically, we make a table, right, of the counts in the categories, or a contingency table, which is just a fancier table that looks like this. And we just talked briefly about this contingency table where we have two variables, right? Variable one is whether this student is looking for a spouse while at university or college or whatever. And variable 2 is the gender. Now, I've arbitrarily named them variable 1 and 2. Unlike scatter plots, it doesn't actually matter which variable goes where, right? Because it's just going to be a table, a two-way table, we call it, or a contingency table, right? And so gender, we're focusing on just 2 categories, and whether they're looking for a spouse, we have 2 categories. And so here, this 86 represents what? Represents the number out of 207 females who were not looking for a spouse while they went to university. Okay. So 86 out of 207. Okay. If we wanted to focus on just what proportion of females, right, we're looking, well, I guess we can do this one. We're looking for a spouse while in college. So they were looking for a spouse, and out of the females, there's 137 total females, right? So this is the total females, regardless of whether they were looking for a spouse or not, right? 137. And so the percentage of females who were looking for a spouse is roughly 37%, right? 0.37. So this is, we're going to talk about this today. This is a proportion. But kind of as a fun thing is that a proportion is a probability, right? So from this sample, we would say, okay, if this sample was randomly selected from the population, then I'm allowed to assume that the probability that a randomly selected female is looking for a spouse is roughly 37%, right? Or 0.37. We do that often where we convert proportions to percentages. So what we're going to learn is that all these 3 P's, we can use them interchangeably. Okay. I say roughly a percentage, right? Because we have to multiply by 100 to get to a percentage. So it's not exactly equal, but roughly. A proportion and a probability, maybe here, must be between 0 and 1. If it's not between 0 and 1, it's not a proportion or it's not a probability. Which means the percentages have to be between 0 and 100, right? Percentages are more intuitive. Our brains work really well with percentages, right? And so if you're communicating results, then communicating the percentages is probably the way to go, right? Usually. Right? And so when we see something like this, your brain probably already converted this to 37%, right? 0.37, you just kind of read it as 37%. Or 37%. Or 26%. How about out of the males? There's fewer males in our sample, right? But if we consider the proportion of males who are looking for a spouse, right, then these numbers are comparable, right? And so now I have 18 out of 70, which is roughly 26%. And the question was, does there appear to be a relationship between gender and whether the student is looking for a spouse in college? Now, at this point in the game, we only have our gut feeling, right? When I look at 26 versus 37, I feel like those are quite different, right? We will develop kind of numerical techniques to figure out if they are significantly different, right? But for now, we just trust our gut and say, okay, well, if there was no relationship, I would expect them to be roughly the same, right? So on average, roughly the same, right? But because they're so different, I suspect that there is a relationship. Yeah. So here, there's arrows all over this page. I gotta stop it. Okay, anyways, if there was no relationship, let's see here, we would expect the proportions to be similar, right? Not dependent on the gender. To be similar. Since 37% is quite different from 26%, we suspect there is a relationship. There is a relationship. Eventually, what we'll have is, can't remember, I think it's section 6.4. So quite a ways down the road, we will have the techniques to analyze it. Section 6.4 will help us analyze this. But like I said, we've got a ways to go, but we will tackle that type of problem. Okay. Any questions before we start chapter 3? Chapter 3 is on probability. And so 3.1 is an introduction to probability. And we're just going to build on this idea that, okay, if I have a random sample and it's representative of my population, then I'll be able to use values from this table, for example, to figure out the probability. Well, a random process is any situation where we know all the possible outcomes. We just don't know which one is going to happen. Okay. So some examples, right? You toss a coin, you know that there are only 2 outcomes, and everyone, yeah, okay, fine. It could land on its side, but we're gonna ignore that for our purposes. Okay, and so, right, either heads or tails for tossing a coin. We can roll a die. Right? So if I roll a 6-sided die, there are only 6 possible outcomes, each with some probability, right? And so, and all these things, iTunes, Shuffle. Does iTunes exist anymore? I don't know. Apple Music, I think it is. Whether the stock market goes up or down tomorrow, you know the outcomes, you just don't know what's going to happen, right? Some rules of probability. Oh, and if you don't have the formula sheet from last day, you come grab it, because it'll have the probability rules. Got it.
Thank you.
Some probability rules. Well, the first one we already talked about, right? Probabilities must be between 0 and 1. Probabilities must be between 0 and 1. How we write that in shorthand is like this. Okay. So the probability of A has to be between 0 and 1. Okay. So how we read this probability notation is you read this as the probability of A. So the probability of some outcome A. So this is a generic placeholder for anything that you want to talk about. Now, usually we use notation, well, it depends on the question, right? It should be kind of clear, but if I'm tossing a coin, for example, then I could say the probability of T, which from context we know would be the probability of tossing and getting tails, right? The probability of T is 1/2, right? 0.5. It's between 0 and 1. And so we'll use this probability notation. And if you grab your formula sheet, we're going to start picking away at this next section, right? So last day we wrapped up the descriptive statistics section. We talked about the 1.5 IQR rule for outliers, right? We don't have time to review it, but that was a lot. There was a lot of procedure there. And you've got an assignment or two to help you nail it down. But now we're going to start probability. So like I said, we're just going to work through this formula sheet. Kind of slow and steady wins the race here. Well, maybe slow for me, maybe, but maybe not for you. Oh yeah, you bet. Oh, I want lines. And I finally figured out how to do it while I was sharing my screen. So that's exciting. So this is from your formula sheet. We've got the general rules for probability models. Just kind of fancy for probabilities in general. We've already talked about this one, right? And so it's on your formula sheet, just kind of help guide you, right? But you should just remember that probabilities have to be between 0 and 1 for any event A. And so I'll keep referring to this as we go through these rules. Or should I just do it now? Wild. Sure. If you had to guess, what do you think S would be? You might not know it as the sample space, but S is the sample space. That doesn't tell you very much, does it? But the sample space is the list of all possible outcomes. So the list of all possible outcomes. Even though we don't know what outcome will happen if I toss a coin, I know that I can either get heads or I can get tails, and those are my two outcomes, and the total probability has to be 1. If I toss a coin, one of those things has to happen, right? So there's a 100% chance, I guess, of one of those things happening from your sample space. Okay. These are going to come up way, way later, but I think it's nice to kind of get them off our plate here. If A is some random event, then A to the power of C is the complement of A. Which is everything that's not A. Everything in S, so everything in the sample space that's not A. So sometimes I read the complement of A as not A. If I tell you that, oh, I sell you a lottery ticket and I tell you, hey, there's a 10% chance that you'll win. What do you also know by that? You know that there's a 90% chance that you're not going to win, right? And so that's the complement, right? The probability that you'll win is 0.1, but the probability that you will not win is 1 minus 0.1, which is 90, right? So our brains already do it, right? We just need to attach some notation to it, right? And so the probability of a complement is going to be 1 minus the probability that it happens. We'll save the rest for later. For us, the interpretation of probability that we will use is called the frequentist interpretation. That's kind of the classical interpretation of probability. Before computers, it's what we had to do. But with the rise of computing ability, we've developed this, or I was not involved. This Bayesian interpretation has kind of come forward. Now, we don't teach Bayesian statistics here. It's the same concepts, just a different approach. And so for us, we're going to be working here, which says that the probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times, right? Which usually equates to however many outcomes you have, you just split the outcomes equally, right? Unless you're told otherwise. So if you toss a coin, you have 2 outcomes, right? So you split that sample space of 1 into 2, 1 over 2. So the probability is 1/2, right? So for many processes, we divide 1 by the number of outcomes, number of possible outcomes. Right, we take that probability of the sample space 1, right, and we just divvy it up amongst all our possible outcomes. For example, the probability, if we roll a die, if I write the probability of a 2, right, then by context, right, I understand that, okay, P of 2 must be, okay, I roll a die, a fair 6-sided die, and the probability of rolling a 2 is going to be 1 in 6, right? We are building off of, okay, if I observe this random process an infinite number of times, then I would expect 1 over 6 of those rolls to be 2s, right? The Bayesian interpretation is kind of cool, where we just kind of pick a number and then we let kind of we let I want to say the computer, but we let the process kind of adjust, and then we revisit, and then we revisit, and then we revisit, and it's not something that we're going to be doing, but it is another way of doing it. But we're getting probabilities either way. Okay. Which of the following events would you be most surprised by? So we've got exactly, now the key here is exactly 3 heads in 10 coin flips. That's surprising, but it's not, you know, the most surprising if we read down, right? What about exactly 3 heads in 100 coin flips? That's very surprising, right? But most surprising would be exactly 3 heads in 1,000 coin flips, right? You don't expect to see that, right? Just because you know that the coin flips should be a random process, right? So you would expect roughly half of the coin flips to be heads. The law of large numbers says that, okay, this feeling that we had, that exactly 3 heads in 10 coin flips, that could happen, right? It kind of fluke, random chance, right? It can happen, okay? But then when we go to 3 heads out of 100 coin flips, then you start thinking, okay, that's probably unlikely, right? And so here in very few coin flips, we expect that variability, right? Everyone grabs a coin. Wouldn't it be so cute if I brought everyone coins? And you flip it 10 times and everyone reports how many heads they got, right? Come to think, I have a bag of pennies in my desk. I don't know why. I've never used them in class, but just in case. So I guess I could have. Game over. Save it for September. Forget. So this law of large numbers says that, okay, if I draw a graph and the number of coin flips, let's say 10 is here, right? So I start with 1 coin flip. Here's 5, blah, 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 blah. Let's put 100 out here. And let's put 1,000 out here. At each step, right, I can record what the proportion of heads, oops, make it an H, is. So if I flip it once, right, maybe it's at 0. If I flip it twice, okay, maybe now I've flipped it 2 times and the proportion of heads, well, maybe the first one wasn't heads and then the second one was. So now I'm here and then here, here, here. So what happens is we get this kind of this scenario. I know, kind of a leap. I'm telling you. Okay. So as we increase the number of coin flips, let me put it, I made it too sloppy. Okay. We expect the proportion to even out. Okay. In fact, we expect it to even out at 0.5. And this should have gone like this. Uh-oh. there. Huh? In fact, it tends to even out as early as kind of 30 coin flips. Right after that, you're expecting on average just kind of 50% heads, 50% tails, right? Or the probability to be 0.5. Now, this is where we introduce our next sample statistic. Okay. So here, p hat, and I'm going to drop the n, okay? But p hat is the sample proportion. The n is just to denote over n coin flips, for example, or over n trials. But in general, we're going to use p hat. So a lowercase p with a hat on top, kind of cute, is a sample proportion. Okay. And what we're trying to mirror is going to be a lowercase p. What we've seen, though, is usually we use Greek letters for the population, right? So overall, this proportion, this population proportion. So if you want, you could use pi, right? If you wanted to. I'm going to use p, and it's the only time that I use kind of a non-Greek letter to denote the population. But pi is also a number, so it gets kind of confusing. Okay. And so here, pi, it's this Greek letter p, which you could use, but I'm going to use a lowercase p to denote the population proportion. Okay. When tossing a fair coin, if heads comes up on each of the first 10 tosses, what do you think the chance is that another head will come up on the next toss? Has to be 0.5, right? This is an independent process. So it must be 0.5. Yeah.
So why is it 0.5 on multiple one?
Because the probability, so here, each of these kind of slots, we'll call them, is a toss, right? And then we record the result. The probability of heads is 0.5, and I got 0.5, right? Or I got heads, and then I got another heads with a probability of 0.5. And then I got another heads with a probability of 0.5, and then I got another one. And then the question is, okay, well, what's the probability that we get heads here again? Like that. Well, that individual heads is going to have a probability. Oops, let's see, clean that up. Probability of 0.5. So it's kind of a common phenomenon, right? You've seen so many heads, right? It has to be tails. No, right? And so it must be 0.5 since tossing a coin, or I'll say each toss is independent of the previous toss. It's called the gambler's fallacy, right? Just kind of, you think that, okay, I've seen this very unlikely series of events, right? But then you have to remember that the next coin toss is just independent. It doesn't matter. It's as if it's happening for the first time all over again. We can build off of this, and I am jumping ahead a little bit, but because we have this scenario built out already, we can find the probability of getting this many heads in a row. Okay. We can calculate the probability of independent events by multiplying each of those probabilities. By multiplying the probabilities. So it is a very unusual outcome in the sense that the probability of this happening is very, very low, but it's not zero, right? You can keep going. And so what would this look like? Well, you have a probability of heads of 0.5 and a probability of heads of 0.5 and another 0.5 and another 0.5. Whenever you find yourself saying and, you're going to be multiplying. Okay. So this has a probability, the probability of 11 heads in a row is 0.5 to the power of 11. 0.5 to the power of 11 is 0.00048828125. Gives it to me in scientific notation. So let me just move my 1, 2, 3, 4. Okay, good. But it's not zero. Right? Small, but not zero. Right? In general, the probability is never zero, right? Unless it can actually not happen, right? The probability exists. It can just be very, very small. Okay. There, I got ahead of myself, but I think it's nice to see. I had a student one summer email me, and she's like, I had this magical Mentos pack. And it was all pinks. And so she sent me a picture of this Mentos package that had the all pink Mentos, I guess, in a row. It was an entire package of pink Mentos. And she wanted to know the probability of that happening. Very small. And maybe I'll bring it in. Well, I don't have it. I have the picture of it. You can see this magical Mentos pack. Probability is small, but not zero. We'd need to know what the probability of each color is, right? But we can assume. Okay. Rewind. We're gonna have this idea of disjoint and non-disjoint outcomes. And so disjoint or mutually exclusive, depending on what you're used to calling it. If you're coming from a different field, you might call it mutually exclusive. I'll use them interchangeably. And so disjoint or mutually exclusive means that these two things cannot happen at the same time. Okay? So they cannot happen at the same time. So the outcome of a single coin toss, you toss a coin once, then it can either be heads or it can be tails, but it can't be both at the same time, right? So those would be mutually exclusive or disjoint events. A student cannot fail and pass a class. It's one or the other. you don't win the lottery and not win the lottery. It's one or the other, right? So those would be disjoint. A single card drawn from a deck cannot be an ace and a queen at the same time. Okay. Whereas non-disjoint outcomes can happen at the same time. You can get an A in stats and an A in econ in the same semester, right? If we think about cards, another example, I'll do a dot to match. A card drawn from a deck can be an ace and it can be a red card, right? There are red aces. A single card drawn from a deck can be an ace and a red card. I'll clean this up. So some things can happen at the same time, right, as we will see, okay? But disjoint outcomes, right, all those probabilities have to add to 1, right, from the sample space that we've seen. So non-disjoint events, the most common example that we use is a deck of cards. Now, sometimes I get people kind of panicked. I don't know what a deck of cards looks like. That's okay, right? I'm not going to ask you a deck of cards question on a test. On an assignment, I can, and I'm allowed to, because you've got this graphic. You can kind of Google it, right? But in general, what are some deck of card facts? These are all face cards, right? Because they have a face on them. So there are face cards. In fact, there are 12 face cards. In a deck of cards. How many total cards? 52 cards. I should have started with that. All right, 52 cards in a deck. There are 4 suits. All right. There are 26 of each color. From this information, why would we care about this? What's the probability of drawing a red card? Be 26 out of 52, right? So the probability of drawing a red card is 26 out of all of them 52, which is going to reduce to 1/2. Right? What's the probability of drawing a face card? It's going to be 12 out of 52. What's the probability of drawing the Queen of Hearts? Must be 1 out of 52. There's only one of those, right? So the probability of drawing the Queen of Hearts, which is this one here, okay, is 1 over 52. Okay. And so then, knowing these individual probabilities, we can build up kind of combined probabilities. Okay. The Queen of Hearts, we call it the Queen of Hearts, but it's really the Queen and Hearts. Has to be both. If we have this image, it helps. Okay? If you're not familiar with the jacks, so the jacks are these guys here. And so if we want to know what's the probability of drawing a jack or a red card, right? Now we're introducing this new term. Well, maybe not new to us, but new in this sense, right? Or can be a jack or a red, and it's also allowed to be a red jack card, right? And so if we were to count, same thing that we did over here, right? We're just counting how many of these cards satisfy this criteria. So then if I have a jack, okay, so a jack or a red card. So if it's a jack or a red, I count it. So I've got 1, 2, 3, 4, and a red card, I've got 26. Yeah. But the problem is that I've counted these guys twice, right? There's overlap here. And I don't want to count those guys twice. They only count once, right? And so what we get is we get the probability of a jack we can write out is 4 out of 52, right? So we know that because there are 4 suits. Probability of a red, we said, is 26 over 52. And then what we have to do is we have to subtract the overlap. So here, we need to subtract the overlap. So we subtract those 2, which have been counted twice, and then we get the probability of a jack or a red is 28 over 52. Nice. Any questions about cards? Counting cards? No. How about a different example? What's the probability that a randomly sampled student thinks marijuana should be legalized? Oh, it's a marijuana heavy day. Sorry, guys. It's weird. It should be legalized, or they agree with their parents' political views. So we've got a contingency table, right? We've got categorical variables, whether they feel like marijuana should be legalized with 2 outcomes, right? Yes and no. And whether they share their parents' politics is a yes and no outcome as well. And so we've got 2 categorical variables summarized in a contingency table. Like I said, we can use this contingency table to find probabilities, right? Assuming that our sample is representative of the entire population of students, yes, then we can use it as a probability. So we want to know what's the probability that a randomly sampled student thinks marijuana should be legalized, or they agree with their parents' political views. If we were to write this out, this is the probability of, can I summarize this as legalize and the complement of legalize, which is not legalize, right? It's going to simplify our notation a little bit, which is pretty common that we do, right? We picked the one thing that we want to talk about, right? In this case, legalize yes, and whether they share their parents' politics. How about we call this politics P for yes, and how about we call this the complement of parents' politics for no? Kind of a jump, but with practice, you'll get there. You could have written it all out in words too, but I want to use the notation. So we want to find the probability that they think that marijuana should be legalized, which is L, or they agree with their parents' political views, or P. Okay. Usually I develop this, but because we've introduced the formula sheet already, let's just go and grab it. Oops. So from your formula sheet, we have this formula for the probability of A or B. So a generic A, B placeholder. So let's grab this, copy. So this is from your formula sheet. Just because I find, or at least last term when I kind of did it properly, so to speak, you develop it and then you introduce the formula. People didn't want to use the formula so much, but it does save you some work. So that's why I want to introduce it. Try something new. It's not new, but. So this is a generic A or B. So you replace it with whatever you're using to denote your outcomes, right? So wherever I see an A, I'm going to replace it with an L. And wherever I see a B, I'm going to replace it with a P in my scenario. Okay? And just like we saw for the probability of a jack or a red, right? We can break it up and say that's the probability of a jack plus the probability of a red, right? The probability of A plus the probability of B. And then you have to subtract the overlap, which is a jack and a red, or just generically A and B. I'll highlight this, that this is the same thing. And so we need to subtract the overlap again. So if we map this question to up here, the generic probability of A and B, I could rewrite this as the probability of L plus the probability of P minus the probability of L and P, right? Subtract that overlap. So loud out there. Okay. That's good for part marks. That's a lot of work. Translating the question into probability notation, mapping it to the formula, right? And so now we need to find the probability that they think that they should legalize marijuana. Now that's going to be regardless of if they share their parents' politics, right? And so that's going to be this 114 out of all of them, 165. So this is going to be 114 out of 165. So here, the probability that they share their parents' politics, that's this guy here, right? Which is 118 out of 165. But notice that I've counted this 78 twice, right? So I need to subtract that overlap, which happens to be L and P at the same time, right? So the probability of L and P is the 78 over 165. Fractions are scary, right? But what's nice is, I'll try to use a different color here, is that we've got a common denominator, right? And so we don't need to do any work finding that common denominator, which means what? I can rewrite this as 114 plus 118 minus 78 all over 165. Which puts me at 114 plus 118 minus 78 is 154 over 165, which is roughly 0.9333, repeating, or 93.33%. The answer is this one. Right. But I wanted to take it all the way. I will say this, if I give you a table like this, you do not need to use the formulas, right? If you were able to get to 154 out of 165 on your own without the formulas, that's great, you did it. Okay, how could you get there, right? You would say, okay, well, they want to legalize marijuana, so that's 36 plus 78, right? And they also have to share their parents' politics, which is plus 40, right? Out of the 165. So you can get there, right, without the formulas, but the formulas will always work, right? And so that's why I want to introduce them, but you'll be able to answer these questions without the formulas. And you're allowed to. Yeah. Any questions about that one? No. So like I said, this is called the general addition rule. Okay. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B, which, I'll say it again, is on your formula sheet. An interesting special case is if you have disjoint events. Then A and B, by definition, if they're disjoint or mutually exclusive, it means that they can never happen at the same time, right? So then the probability of A and B is 0, okay? Which means that if you have this, right? If A and B are disjoint, then the probability of A and B is 0. Then you get a special case, right? But you want to be careful, right, that you always start with this general formula because it's likely that there is some probability of A and B, right? And it's tempting to just add up the probabilities, but then you forget to subtract that overlap. Okay. Wait. Any questions? Okay. Look at us picking away at this formula sheet. So here, this next part isn't until the next section, so we're gonna breathe easy for a little bit, although we might talk about independent events, but kind of picking away at it. A probability distribution lists all the possible events and the probabilities with which they occur. And so the probability distribution for the gender of one kid, every time I use this, I think it's so funny to think of a kid as a baby goat. Isn't a baby goat called a kid? Because I feel like if we're talking about human children, we should probably call them children. But just for some humor, let's say this is a baby goat. It's just cuter. Doesn't matter. One kid. Sounds so weird. But not when you're talking about a baby goat. You've got one baby goat. It's either male or female with a probability of 0.5, 0.5. Okay. So this is what we call a probability distribution, right? Only one of these will happen, right? Because they're disjoint. I know, but for simplicity, right, we'll call them disjoint, right? And so now there are some rules for these probability distributions. The events that you've listed must be disjoint, right? They can never happen at the same time. So it's either one or the other, we just don't know which one. Okay? Each probability has to be between 0 and 1. Right? And so 0.5 is between 0 and 1, and so 0.5 is also between 0 and 1, of course, because they're the same. And finally, the probabilities have to total 1, which means that the events listed must be all possible outcomes. The events must list all possible outcomes, which we already know. We haven't introduced it here, but we already know is called the sample space. What if you have 2 kids? Right? Then the first one might be male and the second one might be male, right? First one might be female, the second one might be female, or the first one could be male and the second one is female versus the first one is female versus, and then the second one is male. These two are different outcomes, right? And so we list all the possible outcomes. We've got 4 possible outcomes. They each have the same probability, right? And how we got to this 0.25, right, stems from these probabilities here for one kid. Yeah. And so here, you can read this as male and male. And whenever we're saying and, which means the probability of male times the probability of male. So that's how we get to that 0.25, because 0.5 times 0.5 is 0.25. Or what's another way? We've got 4 possible outcomes, right? And I have a 1 in 4 probability of landing in one of those quadrants. That's the same. We've just split the probability of 1 into 4 possible categories. Okay. Good. In a survey, 52% of respondents said they're Democrats. What's the probability that a randomly selected respondent from the sample is a Republican? Now, we know that, okay, you're either Democrat or Republican, but there is an option for independents and other things, right? And so we don't want to jump the gun and say, okay, well, it must be 1 minus 0.52, right? And so, so you don't want to use this one, right? Because we could have other parties. It can't be more than 0.48, right? Because then the total probability would be more than 1, so that's bad. It can be less than 0.48, less than or equal to, I'll add, because then it's more of an obvious choice, right? It's not necessarily less than, it can be equal to if everyone just chose one of those two parties, right? But we don't know. But when I added the or equal to, then we're allowed to pick it. Otherwise, I feel like it should maybe be the cannot calculate, just because we don't know how many parties there are, but we're comfortable picking this one. I don't like to pick these ones. It's never that one. All right. Sample space. We've already introduced it, right? And so the sample space is the collection of all possible outcomes of a trial. And so a couple has 1 kid, 1 baby goat. What's the sample space for the gender of this kid? Well, the sample space, S, is, we're going to use a capital S to denote the sample space, is going to be, and I'm going to use set notation here. It's not, we don't need to. You can just list them, right? But use curly brackets to denote the set of possible outcomes. That's not something that I'm going to test you on, so don't worry about it, right? You could just write male or female. And a couple has 2 kids. Well, we already saw what it was. So in that case, 2 males, a male and a female, which is different from a female than a male, or female, female. So the sample space is denoted by S. Complementary events. We already introduced the complement. So complementary events are 2 mutually exclusive events, so they can never happen at the same time, whose probabilities add to 1. Little typo here. There's more typos, but can't catch them all. A couple has 1 kid. If we know the kid is not a boy, then by the sample space, right, we can look and say, okay, well, it's not a male, therefore it must be a female, right? And so they're complementary outcomes because there are only 2 possible outcomes. A couple has 2 kids. If we know that they are not both girls, what are the possible gender combinations for these kids? And I'm just going to copy this here. Copy. So we're told that it's, they're not both girls. So then the possible outcomes are male, 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 female, and then female, male. Right. Good. And this is no longer the sample space. There's something I wanted to say here. Oh yeah, what's the probability of not both girls? A couple of different ways that we could do this, right? I could say, okay, well, I've removed 1 out of the 4 possible outcomes, leaving 3 out of the 4 equally distributed outcomes. And so it's going to be 3/4, right? 1/4 or 3/4. Or what could we do? The probability of the complement of female-female. The complement from your formula sheet, the probability of the complement is 1 minus the probability that it is, which is, I'm gonna need more room here. I don't have a ton of room. 1 minus a quarter, which is 3/4. Same thing. So 2 different ways that you could get to that probability. Yeah. Independence. Independence is going to be different than disjoint or mutually exclusive. Okay, and so the independence says that 2 processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. In fact, I'm going to add about the probability of the outcome of the other. So independence has to do with the probabilities. Right? Knowing that I've tossed heads 10 times doesn't change the probability of heads on the next try, right? The probability stays the same. Versus if I have drawn 2 red cards from a deck of cards, right? That changes the probability that my next card is red, because now I have fewer red cards and more black cards than I did. Well, I have the same number of black cards, I guess, that I did initially, right? And so those would be dependent events, but it has to do with the probabilities versus disjoint has to do with the outcomes, right? Can the outcomes happen at the same time? Has to do with the outcomes, right? If they're disjoint, the probability that they happen at the same time is 0 versus independence, right? Does knowing that something has happened affect the probability of the next thing? Knowing that the coin landed on a head on the first toss does not provide any useful information for determining what the coin will land on the second toss. Okay, and so that's what tells us that the outcomes of 2 tosses of a coin are independent. They're independent events. Knowing that the first card drawn from a deck is an ace, right, does give us useful information for the probability of drawing an ace in the second draw, right? Because now you have to adjust the probability of drawing an ace. The first card that you draw, the probability of drawing an ace would be what? 4 in 52, right? Versus, okay, then you've removed an ace, right? And now you only have 51 cards left, right? And so now you have 3 aces left out of 51 cards. Okay? So let's write that out here. So the probability of ace on the first draw is 4 in 52. Yeah. But the probability of an ace on the second draw, knowing, we're going to change that to given, but knowing the first card was an ace, is now I only have 3 aces left in the deck and I removed a card. That's probably the hardest part, is remembering that now you only have 51 cards to draw from. Right? So knowing the outcome of the first draw affects the probability on the next draw. There's an assignment question that always gets people. I think you're drawing socks out of a drawer or something like that, right? You've got different color socks and you just pull out randomly, and then knowing that your first sock was a blue sock, right? That affects the probability of the next socks because now you have one fewer sock in your drawer to draw from. It could be Skittles or whatever, but this particular one uses socks. Okay, so those would be dependent probabilities. Okay. Gun control. All right. Between January 9th and 12th, 2013, Survey USA interviewed a random sample of 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime, that's a total run-on sentence, or makes society more dangerous. So we're giving them two possible responses. And 58% of all respondents said it protects citizens. Right? What could you do? You could take this information and you could generate a table. What? You could reverse engineer it. Okay. So we've got two possible outcomes. This is more an exercise of the mind. I know, stop doing that, Emily. We've got your survey responses. How can I summarize it? Protects and the complement of protects. So do that. Right. Only gave them two options. Okay. So what we're told is that I might need more columns there, but our sample size was what? 500. And 58% of all those 500 respondents said that it protects citizens. So what you could do, in theory, right, is reverse engineer that 58%, right? Take 0.58 times 500, and you get, they've probably done some rounding, that's okay. 0.58 times 500. They used nice clean numbers. Yeah. So overall, 290 out of those 500 said it protects citizens. This one's so wordy. It's another one where I'm like, I gotta change this. Too much reading. We also collect, or I guess they also collected race. We've got white respondents, black respondents, and Hispanic is usually in there. So now 67% of white respondents. Now we don't know what the total number of white respondents was, so we're not going to be able to reverse engineer it, but we are told that 67% of the white respondents. Okay. Which means what percentage of white respondents said it doesn't protect? 100 minus 67. or 1 minus 0.67 if you prefer. So this puts you at 0.33 or 33%, I guess I should say, right? Because it's out of the white respondents. And so that means that these totals have to add up, right, to the overall white respondents, right? And so you don't want to be adding across here because it's not going to work that way. Okay? And so it's of white respondents. Okay? And maybe I should rewrite this as 33%. Making 100% for those percentages. Okay? 20, let's use blue. 28% of the black respondents, which means 1 minus 0.28, same deal here. Just comparing those percentages, right? Do we suspect that there is a relationship maybe between race and how they feel about if it protects blah, 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 blah? Gun control. I think so, right? 67% versus 28%. And what am I comparing it to? I'm comparing it to this overall 58%, right? If there was no relationship, then I would expect all these categories to be roughly 58%, right? But there's quite some variation. And then finally, let's use green for Hispanics, and 1 minus 0.64 puts me at 36% of Hispanics. Opinion on gun ownership. So this was extra. This was an exercise of the mind, as I said. But that's usually how I would give you the information. And then you would need to translate it into what's in the blurb. So being able to move back and forth is really useful, right? And so opinion on gun ownership and race, ethnicity are most likely, I'm just going to tell you that the answer is dependent. Why? If they were independent, right, we would expect each of the categories to be close to 58%. If they were independent, we would expect each category to be close to the overall 58%. Doesn't have to be exactly 58%, but roughly, right? Since they are very different, we suspect they are dependent. Could phrase it another way and say, okay, if I know that I have sampled a Hispanic person, right, that is going to determine the probability that they said that, yeah, it protects our citizens or whatever, right? Whereas if I say, okay, I have sampled a Black person and that affects the probability of them saying, yes, it protects blah, blah, blah. Got to make it less wordy. Ugh. Okay. And so that's the idea, again, the contingency tables, and this idea of independent outcomes. I don't think I named it, but we're going to use what's called the chi-squared test of independence in section 6.4. So you have to wait until that long until we have kind of mathy ways to figure out if they're dependent or independent. But we've got our gut for now. Let's talk about this notation. The probability of A and then a vertical bar B. That vertical bar is given. So you read it as given. So the probability of A given B. So knowing that B has already happened, right? Then what's the probability of A? Yeah. So if probability of A occurs, given that B is true, right? If we kind of think about it backwards, then if A doesn't care about B, right? If it's not impacted by B happening or not, right? So then we would say that they're independent events. And so if the probability of A given B is the probability of A, then we say that they're independent, which is on your formula sheet in some way. So on your formula sheet, I guess we're just going to get there. Crazy. So this is, I'll just put it really small here. On your formula sheet, we have this. And what I'm talking about right now is the special case. If A and B are independent, then what we can say is the probability of A and B is just going to be the probability of A times the probability of B. That's cool, right? We used that initially when we had that list of 11 heads. And then we said, okay, well, because each of these probabilities are independent, then I can multiply them, right? So it even extends past just two outcomes, right? As long as they're independent events followed by each other, then you can multiply those outcomes or those probabilities. This is really the only formula that you'll really need, which is the conditional probability. And it's the probability of A given B, which you can rewrite as the probability of A and B divided by the probability of B. How I remember it, you don't have to remember it, but I kind of map. Let's do the B's first. A and B, I guess it doesn't matter. And then divided by the probability of B. Helpful if you remember it. So the probability of A given B is the probability of A and B divided by the probability of A, or probability of B, sorry. We already talked about this on the previous, when we made our table and things, but if we said, okay, the overall probability that it protects citizens, right, is 0.58. And so then we've got all these given probabilities, and because these are all different from the overall probability, then we suspect that there's a relationship or they're most likely dependent, right? Because it varies. Okay. We're going to talk more about conditional probability in the next section. So it's all conditional probability, but wanted to introduce it here because they use the notation, which we need. Okay. Blah, 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 blah. No. I'll give you the answer there, but let's go to the product rule for independent events, because this one we use a lot. Yeah? So the probability of A and B, if we have independent events, is the probability of A times the probability of B, which you've seen on your formula sheet. Okay. Doesn't mean anything yet. But if you want to find the probability of A and B, then you can multiply them, assuming that you have independent events. Right? And so whenever you see the word and means multiply, right? So whenever you see or you catch yourself saying and, you're going to multiply these probabilities. And we can extend it, right? I can have k possible outcomes, probability of A1 and A2 and A3 and A4 all the way up to AK, right? The probability of heads and heads and heads and heads all the way up to the 11th head. So here, the probability of heads, 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 da 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 da, all the way up to heads. 11. Just denote how many heads there were. We said was 0.5 to the power of 11, right? Because they are independent outcomes. But we'll start here. If you toss a coin twice, what's the probability of getting 2 tails in a row? And so if 2 things have to happen in a row, usually what I do is I make these kind of slots. And I write the outcome below and the probability above. So if I need, what's the probability of getting 2 tails in a row? So I need a tail and and notice, so you want to catch yourself saying that and, right? A tail and a tail, right? You're only going to have 2 options, and or, okay, in terms of math, okay? And so tail and tail, probability of a tails is 0.5, and makes multiplication, and the probability of a tail again is 0.5. And the probability of a tail and a tail then is 0.5 times 0.5, which is 0.25. Half of a half is a quarter. What's kind of nice is that this method works even for non-independent events, okay, or dependent events, as long as you've adjusted your probability up here. Okay. But we're just focusing on independent events for now. Do I have an example? I don't. Let's use this one. Gallup does all these fancy surveys. They're a huge survey company. And so a recent Gallup poll suggests that 25.5% of Texans do not have health insurance as of June 2012. Assuming that the uninsured rate stayed constant, what's the probability that two randomly selected Texans are both uninsured? Okay. So first, right, we want to find the probability of being uninsured. Now, what's one kind of leap that we're going to make is that randomly sampled Texans are all independent of each other, right? And the probabilities are independent, but that's okay, we can do that. So the probability of uninsured, I'll call it U, is 0.255. Whenever we're working with probabilities, right? Probabilities have to be between 0 and 1. So even if they're reported as percentages, which they often are, right? You want to bring it back to a proportion between 0 and 1. Okay. What's the probability that two randomly sampled Texans are both uninsured? So now I have Texan 1 and Texan 2. Each with the probability of 0.255. Which is going to be 0.255 to the power of 2. Whatever that is. What's this probability? Focusing here. This is the probability of two randomly sampled Texans having insurance, right? Because this is the probability, well, the 0.255 is the probability of being uninsured. So then the opposite would be 1 minus 0.255, which is the probability of being insured, right? And then I have 2 in a row, multiply them together. So this here is the probability of two insured Texans, randomly sampled Texans. So disjoint outcomes, remember, is the mutually exclusive, so they can never happen at the same time, versus the complementary outcome, which is just everything that's not the outcome that you're talking about, right? So in the previous example, right, you're either uninsured or you're insured, right? There's no more outcomes, but sometimes there are more outcomes than that. So do the sum of the probabilities of two disjoint events always add up to 1? Oops. Not necessarily, right? You could have more than two events in the sample space, right? If we had an additional outcome that we haven't considered. Do the sum of probabilities of two complementary events always add to 1? Yes, by definition. Right, because the probability of the complement of A is 1 minus the probability of A. If you rearrange this, right, then if you add the probability of A to both sides, it does equal 1. And that's by definition. If we were to randomly select 5 Texans, which is kind of a funny thought, what's the probability that at least 1 is uninsured? At least 1. Okay. So if we've selected 5 Texans, okay, what are the possible outcomes? You could have 0 uninsured. You don't want to forget about that 0 option. There's a probability that all of them have insurance, all 5 have insurance, right? So you don't want to forget about that 0. You could have 1 out of 5, you could have 2 out of 5, you could have 3 out of 5, you could have 4 out of 5, or all 5 of them could be uninsured, right? Those are all the possible outcomes. S. And so by listing all the possible outcomes, right, we can identify which ones satisfy the criteria that we're interested in. And so what's the probability that at least 1 is uninsured? And so at least 1 is going to be 1 or 2 or 3 or 4 or 5. Okay? So whenever you're saying or, means addition in math or in stats. So whenever you catch yourself saying or, right, it's not going to be 1 and 2 and 3 because it's only one of these possible outcomes. But we need to consider all of them individually and then add them all together, and that's your total probability. So what we can do, we could find the probability of 1, add it to the probability of 2, add it to the probability of 3, add that to the probability of 4, and then add that to the probability of 5. How do you find the probability of 1? Let's practice. Looks like this. 1, 2, 3, 4, 5. 5 randomly selected Texans. Doesn't matter where I put that 1 individual, right? And order doesn't matter in this case. And so I'll just make the first Texan uninsured at a probability of 0.255. And 1 minus 0.255 is 0.745. 0.745. 0.745. Hopefully I did that right, 0.745. Right. Which is 0.255 times 0.745 to the power of 4. I'm multiplying, right? Because if in order to have 1 uninsured, that's my scenario, right? Then and an insured and an insured and an insured and an insured. And so if I multiply these, I get the probability of 1, which is 0.07855345141-ish. You'd have to do that. So that's doing it for the 1. And then you do it for the 2. And then you do it for the 3. And then you do it for the 4, and then you do it for the 5. That's a lot of work, right? And so whenever you catch yourself, oh, that's a lot of work, you start looking for shortcuts, right? And the complement is usually the way to go. And so what if we just lump all these into, so we make the sample space 0, or all of these ones are at least 1. I want to find this probability. Right, but the easiest way to do that is going to be the probability of at least 1 is going to be 1 minus the probability of 0, right? The complement of at least 1. Now you just need to find the probability of 0 uninsured and then remove it from 1. Right? And so the probability of 0 uninsured is going to be 0.74 to the power of 5. 0.745 to the power of 5, which is 0.22949929992, blah, 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 blah. So now the probability is going to be 1 minus 0.229499292. Point 7705007007008. Which, if you kept all your decimal places, you're storing things in your calculator, or maybe using Excel to keep all your decimal places. If you went out and you did 1, 2, 3, 4, 5, and you added them all up, then you would get this answer. You would get that same answer. So you could do it for practice, for fun, maybe not fun, but right. And so nice. Okay. Good. So that's how we use the complement usually, is to shortcut our calculations, right? What if I can think of a complement that's easier to calculate, right? And because we're looking at the entire sample space, right? That's what we're using to say that all of this has to add to 1. So what if I just subtract the one that I don't want? Then I'm left with the probability that I do want. Good. They got so sloppy. Just rounded like crazy. Let's see here. Let's do this one for review. Try on your own for Friday. There. You can try it, and then we'll use that for review next day. If you have any questions, let me know. Otherwise, see you Friday. Stop this here.